Welcome back to Mechanics and Control of Robotic Manipulator. The last class we started what you call differential kinematics, and in the last class itself I said that the next class we will see what is we call velocity propagation. So this particular lecture is focused on velocity propagation. So where we can actually like first start with very general, then we will actually like go with the specific examples. Okay. So in that sense, let us actually like move to the slide. So we will actually like going to talk about general what you call introduction. Then we will see velocity propagation. This velocity propagation would be so both angular and as well as linear. So both linear and angular velocity propagation in the sense, so the base joint to you can say nth joint. So in the sense the base to end effector we would be doing it. Okay. So that is what we are actually like trying to see. Then we will be seeing one of the simple example. Later on we will see few other examples. So the example here we are going to consider is so 2R serial manipulator. So I should not actually like call 2R, but because 2R means it is actually 2 rotary joint, but it's supposed to be called RR. Okay. So this particular manipulator will take as an example and see. Okay. So let us actually like move the general. General is actually like what? So we know like the general spatial motion can be written in the form of this. So what that means? So you have actually like a frame, you can say A, and there is another frame actually like a B, which is you can see like this is rotated. So now there is a point Q. So if this is the case, we can actually like write so this vector Q with respect to B, and this vector actually like we call position vector of B with respect to A. If that is known and this rotational matrix information is known, then I can write the what you call the position vector of Q with respect to A frame in this form. But now what we are going to do, we are actually like trying to talk about what you call differential kinematics, right? So for that what we can do, we can actually like differentiate this equation. So what it comes, we can actually like see. So what you can actually like see the dot nothing but so dp by dt I am writing as a p dot. Okay. So dr by dt I am writing as r dot. Okay. So this is the case. So now if that is the case, if you are actually like differentiate this equation with respect to time, so this dot will come and this is also dot will come. Okay. So then this you can differentiate, this would be actually like function of both. So in the sense this is also function of time and this is also function of time. So first we will take the position derivative, then we will actually take the rotational matrix derivative. So if you are actually like looking at this is the final equation. Okay. So in this equation we can actually like take it one thing. What the one thing? So instead of general plane motion, if it is actually like pure so translation. So if it is actually like pure translation, what that means? So the rotation matrix is actually like identity matrix. Okay. So in that sense what it becomes, so this P of Q A dot become P of B A dot plus, so this is identity matrix, so this will come, so Q and B. Since it's identity matrix, this rotational matrix derivative would be 0, right? So that is the case. So in the sense what you can see, this is actually like two velocity update. In the sense you have actually like one velocity and there is another velocity. So what you can do, you can take the vector addition. Okay, that is what this case. But if it is actually like pure rotation, okay, so if it is actually like pure rotation, what it will give? So if it is actually like pure rotation, so this is actually like simplified as this. Okay. So if it is actually like pure rotation, it is simplified like this. So if you take a derivative, so this is what going to come. Okay. Okay, this vector would be having independent plus, so this r b a dot p q b, right? So now this is actually like for pure rotation. But what we know like r, can I actually like find r dot in some other form? So this is probably one of my concern. So can I actually like do it? So for that we are actually like taking a one simple idea. So what we know, so R inverse is actually like identity matrix. but we know R is actually like orthogonal matrix in the sense you can say the determinant of R is actually like 1. So in that sense, what you can write, R inverse can be R transpose. If that is the case, what you can write, R transpose equal to I. So that is what I have taken. Okay. So now what I can do, I can differentiate this. So what that actually like eventually give. So differentiating with respect to time of this. So this will give R dot R transpose plus, so R, you can say R transpose dot equal to 0, right? So this is what you will get, right? So but what this, so you can actually like take this transpose throughout. So what I can get, R dot transpose plus R dot R transpose whole transpose equal to 0. So what this, so you might have actually like studied about skew symmetric. Okay, skew symmetric matrix is nothing but, so where S transpose equal to minus of S. So in the sense S plus S transpose equal to 0. So this is very similar to that form, right? So this I can write as S, and this is actually like S transpose, it is equal to 0. In the sense what? So S can be written as R dot R transpose. So in the sense you can actually like write R dot R transpose as a skew symmetricity matrix, or what you can actually like take the R dot, okay. So I'll actually like take this R dot as the skew symmetricity matrix, okay. So this is pre-multiplied, okay. I'll just so then you can actually like this inverse, right? From this equation I am writing R dot R transpose equal to S, right? So now I am looking at R dot, so then I can actually take S R transpose inverse, right? But what is R transpose inverse? That is nothing but R only, right? So this can be written as this, okay. So now you need to actually like write this skew symmetricity matrix. The skew symmetricity matrix here is actually like only 3 cross 3 because your rotation matrix is 3 cross 3. So in the sense you can actually like write this is, I can write as probably some omega z, then omega y and minus omega x. So this is 0 0 0, diagonal would be 0 and the opposite is actually like a positive, okay. So this is the way I can write. This is some skew symmetricity matrix. So you can see the diagonal is 0 and the off diagonal term is actually just opposite sign, right? So then it will give S transpose is minus S. So now this policy we can do it, okay. So that is what we are actually like trying to do it. So in the sense I am rewriting this equation in your benefit form. You can see I have rewritten this, and this I have written as a skew symmetric matrix form, and where R dot I can find as S into R, right? So this way I can do it. So this is one way. The other way actually like people used to do is something like this. So I know R and P, okay. I'm just taking a random R matrix which is actually like rotated about Z axis. So it is having this and the position vector as like this. So now what this equivalent? So this equivalent is actually like something. So Px cos theta, right? So then minus, so Py sin theta is the first vector. The second vector is actually like Px sin theta plus Py cos theta, and the third one is actually like simple Pz, right? So now you are actually like assuming that the Px equal to constant and Py equal to constant and Pz equal to constant, okay. So in the sense what we are trying to say, Px dot would be 0 and Py dot would be 0 and Pz dot would be 0. In other way around, it is actually a constant, so the P vector would be 0. That is what we are trying to do. So now if I actually like differentiate this, so R dot P, what it will come? So I can rewrite this. So what would come? So Px dot would be 0, so I am not bothering. So in the sense Px, so the cos theta is having function, so minus sin theta, so theta dot, and this would be minus, sorry, this would be actually like minus, so okay, so minus So minus I don't know, like so minus py, so minus py, so minus py actually like a cos theta and theta dot, I'm sorry. So then actually like in the bottom actually like a px actually cos theta theta dot, and the second one is actually minus py sin theta theta dot, and this would be 0, right. So like this you will come, or you can actually like do it this differentiation, so that is also there. So I am just doing it first differentiation of this, okay. So I will actually like show and come back. So now this is the equation which we obtain, right. So this equation I can actually like rewrite in the other way round. So what other way around, you can actually like multiply this. So it has actually like px cos theta minus py sin theta, then this is actually like py sin theta, sorry, px sin theta plus py, so cos theta and pz, okay. So this is one vector if I multiply. So this I actually like take a you can say cross product with the theta dot, okay. So what that will give, that will give actually like so I j k, okay. So then this would be having 0 0 theta dot, and this is actually like a px cos theta minus py sin theta, right. And this would give so px sin theta and plus so py cos theta, and this is pz, and you can actually like see this term, you take it. So in the sense you take you can actually like, so I'll actually like multiply. So I, it will come, so what would come, so it is actually like minus theta dot, so px sin theta plus py cos theta. So that is what we are also getting it, right. So then the j vector would be, you can actually like see what would be the j vector. J vector would be again so theta dot, so it is actually like minus of minus plus, so that's why I have actually like taken that way. So px cos theta, okay, so plus so py sin theta, right. So like this I'll get minus this minus, right. So now you can actually like see the k would be 0 because it is actually like k. So now this is what we obtained in the previous equation, right. The same thing we are obtained in two forms, right. So in the sense what you can see, if I actually take r dot p in the other way around, where so 0 0 theta dot cross with r p, so that is also like giving the same relation what you are actually like did in the previous case. So in the sense what you can see, so you can actually like write r dot p as something like omega cross r p. So that is what we are actually like trying to find. So you can see, right. So now the previous equation where r dot p I have written as actually like omega, which is angular velocity vector, multiply with the, you can say r cross r, you can say r multiply with p. So this is one such case. So in fact if you recall your general dynamics, so for example this is actually like rotating omega and this is the r, so your position vector goes like this, so which is r vector, and this omega is actually like with respect to z axis. So now this cross product will give the tangential velocity, which is what you call linear velocity, that would be omega cross r vector, right. So that is what we have actually like seen, which is nothing but v, if it is pure rotating. So in this case this is for pure rotation, and this is actually like pure translation with rotated frame, and this is actually the frame translation. So this is pure translation with respect to rotated frame, and this is pure translation. So in the sense this has a slip velocity, and this is having a slip velocity, but it is actually like in a different frame. So you are converting into the frame, and this is a pure rotation, okay. So that is what the idea. So here I should write this, okay. So now whatever I have written, this is actually like rotation matrix of B with respect to A, that you please remember. I missed that syntax here. So now you can see like this is the general motion, so which we are going to use further and further, because we are going to talk about velocity propagation, right? So you should actually like remember, so there will be actually like slip velocity plus, so you would be having a tangential velocity. These two components should be known. So let us come to the velocity propagation stage. So you can see like there are three links. So I call link, you can say this is link I minus 1, this is link I, and this is link I plus 1. Okay. So obviously what one can actually like expect immediately. So this would be actually like the axis I, and this would be the axis I plus 1, right? So now if I actually like separate only this link I, so what I can see, that would be having ith axis and I plus 1 axis, right? So now I assume that this is actually like fixed and it is having some angular velocity omega I, okay. This omega I is actually like referred with respect to this coordinate. So now you can see that this is having an independent motor, we assume it's a rotary. So in the sense it would be having a, so theta dot I plus 1 would be there, right. So now if I want to know the you can say angular velocity of this frame, okay, with respect to this frame. So what I need? I need angular velocity of I plus 1 with respect to I frame. So what that would be? So that would be simple. You can see that you know already omega I, right? That is actually like with respect to this, plus what you have. So there is additional angular velocity at the z axis. So in the sense you have 0, 0, theta dot I plus 1, but that is with respect to I plus 1 frame. So what you can do, you can actually like take the rotational information, right. So this is actually like giving the you can say angular velocity of omega, or you can say angular velocity of I plus 1 with respect to I. But what one can actually like see, so you know the base, right. So the base, or you can say 0th frame. So 0th frame, we can actually like always assume that the angular velocity 0 as 0 vector, or we can assume that it is actually like put it on a mobile frame. So you know this angular velocity. In the sense, so what exactly unknown? So you don't know like what is the propagation, in the sense what is actually like omega 1 and omega 1, right. So omega 1 with respect to 1 you don't know, but what we have a relation. So we have a relation omega 1 with respect to 0. Can I actually like convert that with something? Okay. So if that is the question comes, so what I can actually like see, so I have already one relation. What relation? So omega I plus 1 with respect to I got it as omega I plus I, and this is actually like rotational matrix of I plus 1 with respect to I. So this is actually like I put it as, so I'll put it as something. So I'll actually like put it this as actually like 0, 0. So theta dot I plus 1, right. So now this information I know. So what I can do, I wanted actually like I plus 1 to I plus 1. So for that what I have the angular velocity information of I plus 1 with respect to I. Now I just convert that from the previous frame, in the sense, so I just multiply this with this. So this will give, right. So this is a simple transformation, right. We have already seen. So this is one of the operator. You know, like in the rotation matrix, we said that the rotation matrix can be used as an operator. So in that sense, so we can actually like see this conversion can be done. So now what we can see, you can actually like multiply this rotation matrix throughout. So in the sense, so I plus 1 I, okay. So if you actually like multiply, so what you will get, so this become identity matrix, right, and this actually like because the previous frame, and this is nothing but omega I plus 1 to I plus 1 frame, right. So, in the sense I will actually like write it this. Right. So, this is what we obtain. So, this is what we call angular velocity propagation. Once you know base angular velocity, you know the rotational information, because you must be having the forward kinematic model is available with you, and your motor speed would be available if we consider as a rotary joint. If it is a prismatic joint, this would be 0, right. So, there would not be any active angular velocity there. So, then this would be actually like modified. That is what this particular equation is giving. So, you can see like if you know the previous frame angular velocity and the current active velocity, then you can find the current angular velocity vector. Okay. So, that is what we call actually like angular velocity propagation model. This is we call forward, because we start from 0 to I or 0 to E or 0 to N. So, in the sense you can see this is what we derived, this equation we got it. So, now instead of this is a rotary joint, so if it is actually like prismatic joint, this become 0. So, that is what we are actually like trying to say. If it is a linear joint, so this becomes 0 and it would be a simplified equation. Okay. The same sense we can actually like go ahead with what you call the linear velocity propagation. Okay. So, linear velocity propagation, what one can see, so this is actually like one link. Okay. So, this would be having a you can see you can say joint axis. So, now we are actually like know the linear velocity of this, and here actually like you can assume that I wanted this linear velocity. So, what this is actually like rotating omega I with respect to I, and this is the position vector of I plus 1 to I. So, what this will give? This will give a tangential and this will give a slip. So, that is what you can say, this is slip and this is a tangential. These all information would be in the frame of you can say I plus 1, in the sense I can write. So, V I plus 1 with respect to I can write V I, because this is the same part of body. Okay. So, then you can see this would be the tangential component. So, this would be available, and you want to actually like change the coordinate, you actually like multiply this throughout, you can say throughout R I plus 1 to I. So, then this if you multiply, this equation will come. Okay. So, again you can see this is the slip due to the previous frame, and this is the tangential velocity due to the previous frame angular velocity and the position vector. If it is actually like a translation joint, or you can say a prismatic joint, what you would be getting? You would be getting additional linear velocity. So, in the sense that would be in a z axis, so that we can actually like just add. Okay. So, now you can see this is the linear velocity of the active joint of the I plus 1 frame. So, then you will get. So, now you can see that if you know the you can say angular velocity of 0th frame and linear velocity of 0th frame, you can find the propagation of you can say 0 to n, both angular velocity and linear velocity. So, this is what we call you can say velocity propagation. So, this is a forward propagation, because we are starting from the base to end. Okay. So, we are actually starting from 0 to n. So, that is why it is called forward propagation. Okay. So, now we will actually like see one simple example, with that we will close this lecture. So, what example? We will take again a 2R serial manipulator, which is actually like EC. So, in the next class I will show you in the MATLAB. So, now this is actually like theta 1 and L1, and this is actually like theta 2 and L2, and this is actually like 0 and 1, and this is 2, and this is a 3 frame, right. So, we have already obtained the DH parameter, and we got individual rotation matrices. Okay. Similarly, we have actually like already obtained the position vectors. So, now once this all know, what we have to do? We have to start the what you call base linear and angular velocity. We assume that the frame is actually like fixed, in the sense this is actually like fixed. So, in the sense omega 0 0 would be simply 0 0, and V 0 0 also simply 0 0, because it is fixed. So, if it is actually like fixed, the frame velocity would be 0. So, that is what the assumption we have taken. So, now we can actually like go ahead So this is the model we know, and what you can see, there is a theta 1 dot exists in the first frame and theta 2 dot is exists in the second frame. These are the angular velocity of the active joints, right. So now we can actually start the first frame in the sense omega 1 1, that I can write 1 0, so omega 0 0 plus, so 0 0 theta 1 dot, right. So now what this would be become 0, so in the sense 0 0 theta 1 dot, right. So we obtain the first frame angular velocity. So that is what we have done. So now once you know what you can do, you can start omega 2 2, so that would be 2 1 and omega 1 1, okay, plus 0 0 theta 2 dot, right. So that is what we have actually like done. So this is also we have done, then finally you will get it. So once you obtain any linear and angular velocity, you have to cross check. So now you look at it here, okay. So this point is having theta 2 dot, but this frame is having another angular velocity. Then if you look at it, this is actually like rotate with respect to this, and the independent motor is rotating on that particular axis. In the sense, the angular velocity on this particular frame would be, so theta 1 dot plus theta 2 dot, that is what it is obtained, and that would be in z axis. So that is what you can see, x axis 0, y axis 0, and z axis is actually like theta 1 dot plus theta 2 dot. So the same way you can actually like extend to the third frame, which is you can say passive frame, which is the tool effector frame. So this is the angular velocity. So this is also clear for you, because so there is no active, you can say, joint here. So then you can see this is a part of the same link. So this link is having theta 1 dot plus theta 2 dot. This is the frame, and this link is having this angular velocity, then this point also would be getting the same. So that is what we have found here, right. So now you can actually like see, we can go with the linear velocity propagation. So we know already position vector, we know already the rotational matrix, and we know the 0th linear velocity and 0th angular velocity, and we know all the angular velocity propagation. So we can actually like propagate v1 to 1, v2 to 2, all those things we can find. So v1 to 1, so this is actually like we know, this is we know, and the position vector we got this. So that you can actually like cross check. So this is 0 and 1. You can see that this is actually like on the same axis, so there would not be any linear velocity. That is what proven here, right. When you come here, what would be the linear velocity you can expect? So the linear velocity would be the tangential, that would be theta dot L1, right. So that would be in if you are actually like decompose into two axes. So this would be coming. So L1, so this is actually like you can see this is theta, right. So L1 theta dot cos theta would be, you can say, y axis, and L1 theta dot sin theta dot minus, that would be x axis. That we can actually like cross check, okay. So now you can actually like see that this is actually like obtained. So we have actually like started from what you call in the base, and you are actually like seeing it, this is the second frame itself. If you bring it to the base, so this is actually like you obtain this frame. So that is actually like true, because you are actually like getting it, this is what your x axis and this is what your y axis, you are getting it proper, right. When you are actually like transforming, you will get what we have written in the previous lecture, so previous slide. So now we can actually try the last one, you get this. So now once you all obtain, what really we wanted the end effector velocity with respect to base, right. So what we have, so we have end effector velocity with respect to end effector frame. So then what we can do, we can actually like multiply that with this. So this will give, right. So this is what we are actually like doing it here, right. So in that case, this already we know, and this information we know, and we can obtain this. So now you can see this is the end effector velocity, you multiply all those things, this is what you obtain. You can actually like cross check what is L. So L this, so your x is this, your y is this. So if you take x dot and y dot, so that would be equivalent to this, right. This is equivalent to x dot and this equivalent to y dot, this is matching, right. So we know already in the last class, we have seen that this can be separated as end effector velocity to the joint space velocity, we can map as a kinematic transformation matrix, which we call in velocity form, so we call as a Jacobian matrix. So that is what we have done. So Vx, Vy, Vz, and I actually like this is I call as a you can say linear velocity component. Okay, so this is the Jacobian matrix, and this is what the you call Q dot. So this is mu dot. But you know this is actually like a 2R serial manipulator. This is working in a planar. That too actually like it is going to be XY you can say positional device. So in that sense you can actually like make it 2D of system. Only Vx and Vy you can restrict. So then this would be the original Jacobian matrix which we obtained. So you can actually like recall in the inverse kinematic model we have done this. So the same Jacobian we are actually like obtaining it here also, right? But here what we obtained through the help of velocity propagation. We did not partially differentiate it, right? So that is what the whole idea. So originally what you have to write, so Vx, Vy, Vz, so omega x, omega y and omega z. So this would be Jacobian of q into q dot. Okay. So this is the case supposed to be. So but what we are actually like restricted based on the system configuration, we have restricted this is only active. So then you can actually like reduce the Jacobian matrix in this form. Okay. So with that I am closing this particular lecture. In the next lecture what we are going to see, we are going to see about the modeling in MATLAB, how we can obtain this Jacobian matrix, how we can obtain individual angular velocity and linear velocity, and then we would be actually like seeing the further end how we can go for a static case. So with that I am saying thank you and see you in the next class with the MATLAB. Thank you.